Ethers are compounds that have the carbon-oxygen-carbon group of atoms with no heteroatoms attached to either carbon. So neither carbon has nitrogen, oxygen, or halogen attached. If so, we'll call it something else. But those carbons may be part of alkyl groups, primary, secondary, or tertiary. Those carbons might be part of a vinyl group. So we would have a group that looks like this with other things attached to those carbons. Or it might be part of an alkyl group. So we'd have a group that looks like this. Or it might even be part of an aromatic ring. So we have the oxygen attached to this special ring. It has a six-membered ring with alternating single double bonds. For now, we'll be talking about the chemistry of ethers that have two alkyl groups attached to the oxygen. The other groups lead to special chemistry that we can talk about another time. The ether functionality is a polar group that derives its polarity from the fact that the oxygen is more electronegative than the carbon. And so on both sides of the oxygen, that oxygen is drawing extra electron density and the carbons have partial positive charge. When you add the vectors, it turns out that this group of three creates a dipole moment as I've shown here, with a partial positive in the region of the carbons and a partial negative in the region of the oxygen. This polarity leads to physical properties such as being polar solvents. Like dissolves like, and so the polarity of ethers allows them to dissolve other materials that are relatively polar. And as we'll talk about, ethers are widely used as solvents in organic chemistry. Ethers have limited solubilities in water, but they have additional solubility beyond what you would guess compared to alkanes because of this polarity of this group and the fact that oxygen-hydrogen bonds with the hydrogen of water. Boiling points of ethers are not really elevated compared to alkanes. Diethyl ether has a boiling point of 35 degrees. Pentane has a boiling point of 36 degrees. Historically, diethyl ether was widely used for general anesthesia for quite some time. It's been displaced by compounds that are less harmful to the human body and are less hazardous. Diethyl ether is highly flammable. Both diethyl ether and tetrahydrofuran are still widely used. They're used as solvents in industrial processes and in research labs. They're relatively similar. Tetrahydrofuran is more polar than diethyl ether. You can see that from their boiling points. While the boiling point of diethyl ether is 35 degrees, the boiling point of tetrahydrofuran is 66 degrees. Tetrahydrofuran, because it's more polar, is miscible with water, while diethyl ether is barely soluble in water at all. Like alcohols, ethers act as bases. A lone pair of electrons on oxygen is available for sharing with a proton taken from an acid, which we can follow with our arrow pushing. As that bond is made, this bond must be broken. It's an equilibrium reaction. The main chemistry of ethers is the chemistry of cleavage. Carbon-oxygen bond cleavage. So you see this bond has broken, and we have a carbon nucleophile bond that has been made here. And finally, we could mention that the chemistry of ethers also is the chemistry of oxidation. But these are radical reactions that we're not going to discuss. The oxidation reactions that are most widely known and of concern are A, combustion. Ethers can be highly combustible. Diethyl ether can be used as a fuel. It's actually used in the engine starter formulations that you can buy at the automotive stores. And ethers also oxidize simply by standing with air to make a hydroperoxide. These hydroperoxides typically are highly explosive. And so the oxidation reactions of ethers are basically the chemistry of destruction, making explosive hydroperoxides and burning with air. We're going to focus our attention on these two chemical behaviors together because you'll see, as with alcohols, protonation of ethers leads to a good leaving group, and that's what accounts for the acid-catalyzed cleavage of ethers to make new products.